So let's do a third way or fourth way of looking at things. And this brings me to what's called Kramers-Moyal expansion. I will not formally develop Kramers-Moyal expansion because I guess you've seen this before and it's not really such a deep thing. Let me illustrate the Kramers-Moyal for the problem we have at hand. So we have a time evolution equation for probability, and now let me allow to not specify the initial condition. Then this Langevin equation has a loss term where we have our rate lambda of n, and we lose from probability Pn of t, but we also gain because our process always goes from n to n plus some delta n, right? And the delta n is this L minus k that we had. Delta n is L minus k. So as I go from n to n plus delta n, I gain probability if I were previously at the point n minus delta n, and I have then the corresponding rate going out of this state n minus delta n. Now when you look at this equation, this is a function, the whole thing here, of n minus delta n. So you can Taylor expand this function to arbitrary order. When you do so and expand this to arbitrary order, the zeroth order term will cancel out by this loss term. So that is the same as the sum from mu equal to 1, in principle to infinity, and here Taylor expansion 1 over mu factorial, partial derivative with respect to n, mu times, and then I'm taking this here lambda of n p of n comma t, and from the Taylor expansion I get the delta n to the power mu. Okay? And that is the Kramers-Moyal expansion. It is just a Taylor expansion, a formal Taylor expansion of the master equation. Okay, now for that Kramers-Moyal expansion that you see here on the board, there's two possibilities. Either this thing stops at mu equal to 2, or it never stops. That's called Pabula's theorem. And it's worked out in the lecture notes when you want to check it. So this stops at mu equal to 2, and then it corresponds to a Fokker-Planck equation, or it stops never. If it never stops, then this expansion is completely useless. It's only useful then, that you do the analysis in the original thing, or it becomes useful if you find a way of writing this as a master equation, or as a path integral. And let me do this now. So for that, let us rewrite this a bit. So let me integrate this over n. So again, as often in these calculations, I use a resolution of the 1. In this case, it's a delta function. Then I have here as well a sum over mu greater or equal to 1. 1 over mu factorial dm mu times lambda of n p of m and t minus delta n to the power k. Okay. Now, what I want to do is I want to rewrite this delta function as a integral over a secondary variable. So I use a Fourier representation of a delta function. That means this is the same as the integral over, what's my variable now? I call this n twiddle over 2 pi e to the minus I n twiddle times n minus n. Okay? We know this is delta function representation in terms of this Fourier transform. Now you have this expression, and here you have derivatives with respect to m, mu times acting on the right hand side. We can shift this to the left hand side by doing partial integrations. Okay, so we do partial integration, mu times. What you then get is an integral over m, p of m and t, lambda of m, sum over mu greater or equal than 1, delta n to the power mu over mu factorial, the integral over this auxiliary field divided by 2 pi e to the minus I, and then from the partial integration I get this. Hope you can see that. So what the partial integration does, it cancels the minuses that you have there, and it pulls down the I n tilde to the power, which is mu here in my notation for the Taylor expansion. And here the same thing. The index of expansion, I call it mu. All right, now you have that expression here at hand, and you can write this in exponential form. So I can also write this as p of mt, because this sum here is an exponential, integral over my auxiliary field. And then you have the lambda of m, e to the minus I auxiliary field, n minus n, and then writing out the sum here over I n tilde and the prefactors gives me I n twiddle delta n minus 1. Okay, and this expression that you have here in the brackets, you can write as a delta function for the first term, which is n minus m minus delta n, so n minus delta n minus m minus delta n minus n. Okay, now let us look at that in its full beauty. Kind of doing calculation in circles here. So we started out from the master equation. We wrote it in a Taylor expansion. Making explicit, I think that's the point, that this is an expansion in delta n. So it's an expansion in small deviations of states. So it's a low noise type of approximation that we have here. And then I was rewriting this in terms of delta functions, like so, and doing partial integration to finally arrive back at my same master equation. Okay, so I could have done this calculation like so right away, And the reason I did it the way I did is to show you that this is an expansion in delta n. So this is T. And the form that we want to use in the following is this one. This is my dt p of n and t. And I want to use this as a starting point to formulate a path. Okay, so that's what we want to do. We want to formulate a path integral. That's our goal. Procedure is the same as always. You write the differential equation in a difference quotient form, and then from the difference quotient form you construct a recursion relation, and you iterate the recursion relation. So let's do that. So from the forward equation now, this is the beautiful thing about this here, I can ratchet myself forward from some time tau to some time tau plus delta t. Then I have my original distribution and the one that's incremented forward, d tau dt p of n tau. Okay. Now I can insert the equation that I have here on top. Okay, so this is the same as an integral over m, an integral over n twiddle. And note, this is a very similar structure as before. We have two fields. One is a field that's directly corresponding to our variable. And the other one, the twiddle field, is an auxiliary field that we have introduced here for the delta function. So this is then 1, this is this one here, plus the delta t. And then I'm just copying the terms that you get. There is a lambda of m. Then there is this e to the I n twiddle delta of n minus 1. And then this factor e to the minus I n tilde n minus m p of m and tau. Okay. So I hope I have all brackets. Okay. Okay, that's what you have. It's just the same terms. And now, again, as usual, delta t is small. I don't account for delta t squared here. This is implicit. I can write this as an exponential. Again, terms that would change that are of higher order. So this is higher order. This here also. And that here is to that order the exponential of delta t lambda of m e to the I until the delta of n minus 1. Okay? And to that, you need to add this one. Okay? And then together, those terms, we already have the action. So that then gives you an integral over m, the auxiliary field, divided by 2 pi. Then we do have the exponential of minus I auxiliary field n minus m plus delta t lambda of m e to the I n twiddle delta n minus 1 p of m and tau. Right, so when you read it together, we have the time, the probability distribution function at a time a little later than tau, and we have connected it via this relation to the earlier time tau by this integral over all the different probabilities for all the states m. It's a recursion relation again. You can reiterate this recursion relation. So insert on the right-hand side what we found for the left-hand side. Do this again and again. That means then as you repeat this recursion relation, you get the full probability density between 2 time points, an initial time t0 and a final time t. This is then an integral that starts from t0 and ends at t. It is integrating all the trajectories or all the paths for the field variables n and n twiddle with the action S of n and n twiddle. The action we can just read off. So with the action S being given by a time integral from initial to final time, d tau. This term here translates itself not into a difference, but a time derivative, d tau n. And the term here is just lambda of n e to the I twiddle delta n minus 1. Okay, so this is our path integral. It's different than the one before, right? This has a similar structure in the first term. Did I get the sign right? Nope. This is a plus. Okay, it has a similar structure as before. We have a double integral over 2 fields. The difference is now that n, right, is the actual number density. Okay. In contrast to x, x was not the actual number density. It was some variable that we defined because we marginalized the distribution over some Poisson distribution. Here n is the real thing. So question that remains is, what do we do with the last term here, this one? Now let us compare with what we have, and ideally with this one. Okay? So this is the Fokker-Planck equation. And we know we get the Fokker-Planck equation from the Kramers-Moyal expansion. When? When we expand things in delta n to second order. So we can do so. We can expand this object here to second order, and then we must recover the Fokker-Planck equation because we're just using a different way of arriving at a Fokker-Planck equation. So let's see that. So to second order, in delta n, we get for the action S equals the time integral, then I twiddle n d tau n. Well, what we get from here is you expand this, the 0th order term cancels out with the 1. Then I have a term proportional to delta n, and that's linear in In. And that I include here in this linear term, linear to In. This is minus lambda of n delta n. Okay. The other term that we get is then plus. So I have here, to be careful now, it's not plus. It's minus a half I n tilde squared lambda of n delta n squared. And now you see this has the proper sign. Okay? This is the minus that you have here, and here it also has the proper sign. So from that, what you do get is for the specific case, so for a plus a going to 0, we can write the equation of motion for the n, which is then dtn equals minus lambda n times n minus 1, because that's what lambda of n then is. It's counting down with this n sub k plus the square root of a positive thing 4 lambda n times n minus 1 times eta. Okay? So we do get the Langevin equation, and it has a well-defined positive definite noise term, kind of, right? Be careful. For large n, this is all fine, it's all perfect, because that's positive and this here is then also positive. Things here become awkward only if n is small. If n is 0, this is 0. If n is 1, this is also 0. So from that approximation, if you go down to small particle numbers, the noise is getting 0, or worse, if you were to be allowed, which you are not, to have n between 0 and 1, then this is negative. So you would have also some negative noise amplitude here. But you don't. This is valid in the sense of a Kramers-Moyal expansion only in the limit of n being much larger than 1. Yeah?
But our jump size was delta n, right?
Yes.
So not integers. So we could end up with 1/2. If delta n is 1/2, we only have jump half integer sizes, and I get an imaginary noise. In between.
No, the delta n's are L minus k.
Okay, so they're not really small. They're bigger than an integer.
Yeah, the expansion, the Kramers-Moyal expansion is formally right if n is large. So it's not the absolute value of the delta n's being small or large, because they're always of the order 1. Right, 5, 6, 7, whatever that is. The point is in the Kramers-Moyal expansion that those jumps are of order 1, and the population sizes you consider are huge.
Fine, okay.
And then this expansion, if you work it out, so if you rewrite this expansion to second order, I haven't done so, but you can do this for yourself, and then define a variable which is the population size, n, in terms of the total population size that you expect, then the drift term is of order 1, the diffusion term is 1 over population size. And so it goes down in the analysis. And that means these approximations here, where I go to second order and map to Fokker-Planck, they are valid if the typical population size exceeds 1 by far.
Okay, right. Because that has a Langevin equation, even the eta is
Yeah.
random variables. If I simulate this, I crash.
Yeah.
Yeah, okay.
So if you simulate this, it's all fine.
If I start big enough.
If you start big enough, if you want to analyze a first passage time to extinction, you will have a problem. Because there, once you add small particle numbers, this is not quite the right approximation as I did the derivation in terms of delta n being small as compared to population size. Okay? So maybe you see it now that in a small noise limit, these systems reduce to everything fine with a Gaussian noise that's positive definite. If you're not in a small noise limit, you have this awkward operator here. And if you expand it out, it not just contains quadratic terms, which would correspond to a Gaussian distribution, it also contains delta n to the third, fourth, etc., etc. And then it's not so clear from that analysis which ones to keep, where to stop. If you analyze critical phenomena, this right-hand side is a series of operators, and there you can again decide on when these terms are important or not, based on the relevance or irrelevance of these terms at critical points. Okay. What else did I want to say? Yeah, let me give you one example at the end. Okay, so we will close this week with what we started the week, and that is the problem of directed percolation. Well, remember you have 3 processes. One is that you have A giving rise to 2A, which is birth. You have A going to the empty set. That is a death event. And you have A plus A going to A, and that is a competition event or a coagulation event. Good. Now let's, for that case, write down the corresponding Liouville operator, Q hat. And I have to assign rates here. So birth is with rate mu. Death is with rate lambda. And coagulation with rate gamma. Okay, so now let's check out whether you have understood how to write this. So what would be the birth event? Mm-hmm. So let's first read this, right? You have killed 2 A's, right? And you create the A. And then you have to subtract from that the process that's the exit rate process, which is simply minus A. So the next one, plus lambda. What's happening there? Also reading this backward in time. The 1, right? This is a to the 0. And then we have a dagger, and I have to subtract an a. And the last one, plus gamma. Here, again, backward. I'm destroying an a. And I'm creating 2, and I have to subtract here the corresponding a squared. So you see it's always like a dagger a dagger a dagger squared, a squared, which is the terms that are subtracted. Okay, so once you have seen this a few times, you know how the recipe works. What's the action that you have? The action, which is now the coherent state path integral action, that's the one which I derived first directly from the marginalized distribution. This is, as usual, a time integral. Then we have IQ x dot. Right? And then you need to include in this term here all the ones that are linear in the operator that we have. So this mu naught minus lambda x plus gamma x squared. And that shouldn't surprise you, this kind of term. So you can read it off from above, but you can also guess it, because that should be the equation of motion in the rate equation approach. You have time evolution is birth minus death times x, that's the linear part, minus gamma x squared, which is the coagulation part. So that's the equation of motion. And then we have the noise terms, and they are quadratic. It's mu x IQ squared plus gamma x squared IQ squared. And here you see there's different signs that appear here because we're not constrained here by any way, by any positivity constraint. All right. Then we can also write this as an action in the Kramers-Moyal path integral. And here I'm writing the Lagrangian. Doesn't really matter, right, whether I write the action or the Lagrangian. It's just I omit now the time integral. So what is that? In that case, you get E and twiddle d tau n minus mu n e to the I and twiddle minus 1 minus lambda n e to the minus I and twiddle minus 1 minus gamma n minus 1 e to the minus I and twiddle minus 1. Okay, and now in this formulation, if I do an expansion, meaning that I'm now expanding in powers of the I to the n tilde, then I get I and twiddle d tau n minus mu minus lambda n plus gamma n minus 1 minus a half I n twiddle squared, and then we have mu plus lambda times n plus gamma n minus 1. Okay. Now you should see that there is no difference really between this term and that term. There's a slight difference because in the formulation where I use the Kramers-Moyal expansion, I get the correct counting, n times n minus 1. If I have calculation, I pick 1, then I can just pick n minus 1 from the remainder. That's why you have an n minus 1 here. But it doesn't matter since this is valid for a large n anyway, only. So this structure here and that structure are basically the same. The difference, the key difference again is that here you have a term that's a Gaussian noise term, and the amplitude of that Gaussian noise term is fine as long as n is large. This is all positive. So that's the amplitude of the noise. And if you were to write this in terms of a Langevin equation, you actually can. Okay. So here for the expanded version, this is mu minus lambda times n plus gamma n minus 1 plus c of n lambda, and the c of n is fine. It's this here. It's the c squared of n. Okay, but the actual problem is different. So if I really want to know what is the critical behavior at the absorbing state phase transition of directed percolation problem, I cannot go here. I have to actually worry about the distinct contributions that you have here that have a different mathematical structure than the one you get. And this is important for the minimization group analysis that you perform. And you do the full field theory always in the path integral formulation. Here you never go back to Fokker-Planck or Langevin because you can't, but you don't need to. You can formulate the full theory for all the correlation functions for that action here. Right. Maybe I stop here and take your questions. As we can, because we have everything now on the board. So we have a bunch of path integrals that we can formulate. For continuous state spaces, it's this, Ito, Fokker-Planck, or path integral with the corresponding Gaussian noise term and the drift term. For the master equation, there is two types of path integrals. There's either this one, which I call the coherent state path integral, or there is one which is of that type here, or where do I have it? Yeah, or it is of this type. This is the Kramers-Moyal path integral. So those are all the forms that you have that you can formulate. And maybe as a short closure, so you see that things are related. There is a mapping that brings you from this one to that action. I'll write it down for you and you can check. So if you do A dagger A, which is equal to x I cubed plus 1, and you call this n, and you set A to I cubed plus 1, and call this e to the I n tilde, known as a Kohlhoff transformation, or also a Grossberger transformation. So if you use that, you can transform the coherent state path integral formulation into one which is derived from the Kramers-Moyal path integral expansion. It kind of tells you that the objects that you have in a coherent state path integral are not the most natural ones if you want to have an interpretation. Right? The interpretation really hinges on n being a real, observable, giving the population size, and the twiddle n here being something like a placeholder for the strength of the amplitude of the noise, because when you expand this out, you get the Kramers-Moyal terms leading to the Fokker-Planck equation. All right. Thanks for your attention.